Hello, good morning. Welcome to We Martians. My name's Jake Robbins. Thanks for hanging out to us today. I am so excited to be experiencing the Mars 2020 launch with everyone today. So if you know my stuff, you follow me a bit, you'll know that I normally do podcasts. And so what am I doing here on this video? Well, normally what I like to do for a launch is go down and watch the rocket. That's what I did for Insight. It's what I really wanted to do for Mars 2020. I had big plans. But of course, that was in the before times, before the pandemic. And, I'm in Canada, and so I'm not even legally allowed to go to the United States right now. So unfortunately, this is what we're doing. But it's actually kind of good because we get to hang out with many more people, all of you virtually right now. So I'm so excited for that. Now, I don't want to just sit here and talk for an hour with you by myself. So I am recruiting help today. So we're going to bring on a great co-host, my good friend, Dr. Tanya Harrison, who is a planetary science, a Mars specialist. So let's bring her up on the screen here. Hello, Tanya.
Hey, Jake. How's it going?
Good. I'm so excited to have you here. So you are a planetary science. You're a Mars specialist. You're a professional Martian, you like to call yourself. Director of science programs at Planet. Is that the title? Did I get that right?
Manager of science programs.
Manager of science programs. You're an author. Is there anything you don't do? Like, what's the deal with all this activity? What's going on here?
I don't do underwater basket weaving, but other than that, pretty much everything else.
Well, I'm really happy to have you. How excited are you for this launch today?
I'm pumped. I was also supposed to be there in person like you, so dang COVID for getting in the way of everything. But, this is really great because we can all still hang out with each other and share it with the world this way.
Yeah, totally. How long have you been following this launch? Because I feel like we've been waiting for Mars 2020 for decades. I don't know. It just feels like forever. It's really weird to me for this to be like a real thing that's actually happening now.
Yeah, I think I'm so used to delays. I wasn't even sure if it was going to launch this summer. Plus, with everything else that's happened in 2020, who knew what was going to happen? So it's like, this is our one glimmer of hope, like something good happened. And we've had a good pattern of launches so far with Tianwen and Hope. So let's hope we go for 3 for 3.
Yeah, totally. So a little bit about logistics today. I'm going to bring up a little bit of a timeline here so you can see what we're going to be doing. So we've got a number of amazing guests to share the stage with today. So in a couple of minutes, we're going to bring on Dr. Alexandra Pontefract, who is an astrobiologist from Georgetown University. She's going to tell us all about searching for life on Mars. And then later in the morning, we've got Nathan Williams coming in. Whoa, I got a typo on the screen there. That's fine. Nathan Williams coming in to talk about, isn't that a comic book artist? Did I really mix up in my brain? Yeah. That's a good one. Nathan Williams from JPL will talk about the Mars helicopter. And then we're going to watch the rocket launch. And then we're going to watch a coast phase. And then Phillip Hargrove from NASA Launch Services is going to come on and talk about trajectories, which is really, really fun. And so that's what we're going to do today. So a little bit about this. And then we're going to have the stream up kind of at various different points so that you can see it as we go here. And that way, if anything crazy happens, we'll be able to jump back to it and make sure we don't miss anything. So this is Mars 2020. This is a sample return mission. It's a big flagship rover, and we're going to learn all about it. So I don't think we're the first guest. We can probably dig right into it right away here. What do you think?
Yeah.
So let's bring on Alex. So Dr. Alexandra Pontefract, like I said, astrobiologist from Georgetown University. Good morning, Alex. How are you?
Good morning. Thanks for having me here. How are you guys?
I'm
Good.
tired.
Yeah, it's very early where you are.
Yeah. Now I'm in Vancouver, so it's dark out still, even in the middle of summer at this high northern latitude. But either way, we're just really, really excited to have everyone here today. Alex, let me kick it off with this. We have been looking for all kinds of different life in various ways. I thought that the search for life was pretty binary. You're looking for it or you're not. But there's actually like a couple different ways that different missions have been doing it. You hear things like searching for signs of life, or searching for habitable environments, or actually looking for life. Can you walk us through sort of what those mean, and then tell us what Perseverance is going to do?
Yeah, that's a really great question. And it is a complicated, very complicated topic. So I would say that it started out with us actually looking for life, for what we call extant life, so life that is living today on Mars, and that began with Viking 44 years ago. Of course, that mission ultimately was deemed not successful, and so we had to take a bit of a step back from that, and we moved to trying to understand not whether or not life could exist on Mars, not whether or not life does exist on Mars, but whether it could exist on Mars. So this marked a shift in NASA's focus on how to look for life beyond Earth, and we started focusing on habitability. We started this process of follow the water. So the last few rovers that went to Mars were focused on this idea of habitability, of if life as we know it could exist on Mars, are there regions on Mars where it could persist?
So that's like Jezero Crater and Meridian and Plan. That's the kind of things they were doing in those areas.
Absolutely. So it's trying to constrain the geology of Mars and the past geochemistry to identify whether or not in Mars's past we had a habitable environment. So, and this brought us to the level today where we know that Mars in the past was very similar to what Earth was and could have supported life.
Okay. So what is Perseverance going to do specifically to do this? Like, it's got some instrumentation, but what's the way it's going to try and solve these questions?
Yeah, so Perseverance, part of the reason I'm so excited about this mission is that it marks a return to the focus that Viking began. And so it marks this shift in NASA's goals from habitability to life detection. Now, I should make a point here that Perseverance is not capable necessarily of extant life detection, with like life that's living today. That's not the main purpose. We're looking for signs of past life, but this is the first time we've returned to that type of exploration. So I'm really, really excited about that. And to do that, Perseverance has several instruments that are equipped to try to answer those questions for us. So an important instrument is something called a Raman spectrometer. And basically a Raman spectrometer allows you to look, allows you to look at molecular vibrations in between atoms, and that gives you a fingerprint.
This is Sherlock, right? Is that one?
This is Sherlock, and actually SuperCam as well. So SuperCam has a Raman spectrometer of a wavelength that's in the visible range. And then Sherlock has a Raman spectrometer with a laser that's in the UV range. And these two different lasers allow different types of investigations. Some are suited better for biomolecules and some are suited better for geology. But basically the Raman gives you a fingerprint of any molecule that you want to look at. So whether it's a mineral or whether it's a microbial molecule, so like a pigment, for example. So this instrument is set to actually look for signs of past life in the rocks. And combined with that, we have Pixel, which is something called an X-ray fluorescence spectrometer. Basically, it shoots lasers at the rock, causes excitation, and then
I love anything that shoots lasers on Mars.
And
There's Pixel on the screen there.
That excitation gives us an idea of the chemical makeup of the rock. And specifically, what we want to look at is patterns, something called redox patterns within the rock. So redox means reduction, oxidation reduction. So that's how microbes function. They transmit electrons back and forth between themselves and the substrate that they're living in, and they leave a signature behind that is different than what you would get if there was no life living there. So with Pixel, we can start to pick up these patterns of differences in chemistry within the rock, and then that allows us to zero in with Sherlock and actually take a map of the same area with a Raman spectrometer and see if we can find signs of past life.
So there's like some complementary work there between the instruments then. Okay.
So life detection, because it is so complicated and because it is so difficult to have 100% confidence in your findings, it's best to have multiple instruments that all support each other, that can all then come to the same conclusion that yes, this is a very, very strong signal of potential life. And at that point, what we would do then is cache that sample. We would take a drill core, cache that, and hopefully have that from Mars sample return.
And bring it home, yeah.
Yeah.
Oh, wow, that's interesting. The geochemistry stuff is like, it's a struggle for me. It's like my my weakest point. Anytime, sometimes I get like a paper in my RSS feed that's like, here's a geochemistry, and I stare at the abstract like, oh my God, how am I going to figure this out? So thank you for
It's not simple.
Yeah,
No, it's
even
not.
for scientists, it's really hard to parse those
Well,
papers.
I was going to ask you, Tanya, because I'm like, you must have to read these like on a much more regular and professional frequency than I do, and I just can't. I struggle.
Yeah, it's not easy. And I mean, I'm not a chemist, right? So for me, it's just kind of like.
So could you tell us about Jezero Crater and why this is a good place to do this mission at?
Yeah, so Jezero is exciting for two reasons. One, personally for me, and I mean, obviously for the Mars community as well, is that it is an impact crater. Impact craters are phenomenal for producing clays, for potentially creating hydrothermal environments when the impact occurs, and for hosting an impact crater lake, as Jezero Crater did. And then what's specifically interesting about Jezero is that there are these preserved deltaic deposits. And a delta is really great because it means you have slow-moving water passing into the crater and depositing a lot of sediment over time. And what happens with this kind of environment when you get this happening is that you have a really great environment for preservation of any type of life that was living in that system to begin with. So that will cement over time. We'll get sandstones, we'll get mudstones, and these are the rocks that we're going to be looking at for signs of past life, just like we would here on Earth.
And we're going to be taking samples here. When we actually get those samples back, 2031 or thereabouts, what are we going to have to do with those to be able to definitively say there was or was not life in those samples?
That is going to be a very challenging task for the scientists who will be looking at these samples. So just to sort of put it into context, I don't know if you remember the Allen Hills meteorite. And when we thought that we found life in Allen Hills meteorite, and that was with.
That's when Bill Clinton came on and said, "We found it," right?
and that was with high-powered, really great analytical instrumentation. It's really easy to make a mistake and to mistake something that's abiotic for something that's biotic. So there are different types of instrumentation here on Earth that are potentially versions of what you would see on the rover itself. They're more high powered. They allow you to get down to finer scale resolution, but it's not something that we could actually send to Mars. So when we bring back, we can look at a higher resolution. So basically, cells like on Earth are maybe the size of about a micron or smaller, and with Pixel and with Sherlock, we can't quite get down to that kind of scale. So we can see patterns if we have a little more than a couple of cells. But if we have just one cell here and there, it's really hard to pick that up. So by bringing it back to Earth, we can look at it at the scale of a microbe and try to see if those patterns are there. And then you would go through multiple lines of investigation. You would look at patterns of geochemistry. You would look at morphology as well, but morphology you have to be very careful about when you're trying to say whether or not it's a cell or not a cell.
Yeah, as we've learned.
Yes. But it's a very difficult thing to do.
Does that mean there's a chance that we maybe see it when we go there with like Pixel and Sherlock, but we can't confirm it until the sample gets back?
That's likely what would happen. So
it's going to be brutal.
It's going to be brutal, but I mean, at the same time, it would be so exciting to see something and say, you know what, this looks really, really promising. This looks like it could potentially be signs of life. I mean, my dream would be to see something like a stromatolitic texture. So like these layerings that you see of cyanobacteria, and well, I mean, you wouldn't necessarily get cyanobacteria, but of some kind of layering where you see layers of cells and then layers of sediment, layers of cells, and then have compacted over time. That would be an incredible find. But yes, it would be very hard to independently verify through just the rover that we have found signs of past life. So that would be difficult.
Cool. Alex, this has been awesome. Thank you for sharing all this information with us. I'm really excited that we get to do this. Hopefully we get enough to make us not have to wait 10 years for some kinds of answers, but we'll see how it goes, and we'll have to touch back with you when we get more on the submission.
I think regardless of the fact that we may not be able to make a definitive determination, I think a lot of the research that we'll be getting back, whether it supports the presence of life or even if it's just information about the Martian history, geological history, is going to be incredibly interesting.
Totally. Cool. Well, thanks so much for joining us today. We really appreciate it.
Thank you. Thanks for having me.
And maybe if we see some of those potential signs of life, it'll accelerate the funding and timeline, try to get the back a little bit faster.
You know, one of the things she said was really struck me is like we have to always remember, like this is it's like this 3-mission Mars sample return campaign, and sometimes it feels like, oh, it's going to be 2031. But like even if like missions 2 and 3 fail, this is still a flagship rover that gets to do a whole bunch of geology and astrobiology in situ right there, and like it adds its own value. So I always have to kind of remember that.
Yeah, even if we don't get the samples back, it's still going to be an amazing mission.
Totally. So Tanya, I thought maybe we would talk a bit about some of the differences between Curiosity and Perseverance, because it's kind of a good common narrative. So maybe can you walk us through some of the instruments that are upgraded from Curiosity? Because like, some of them are kind of like iterated, and maybe just give us a quick high level overview of what those are, and then we'll talk about some of the engineering after that.
Sure. So my area of expertise is cameras. So the big difference that we've got is a larger suite of cameras on this rover. We had 17 on Curiosity, and there's 23 on Perseverance. And Perseverance was equipped with, or is equipped with, the Mastcam Z cameras that we were hoping were going to be on Curiosity. So we would have this pair of zoomable eyes to be able to get stereo of everything that we took images of. Unfortunately, those ended up getting descoped from Curiosity, and we ended up with the fixed focus cameras that we've been getting images back from for the last few years. But we have the new and improved version of Mastcam Z on Perseverance. And so we'll get all of these great stereo views with these color filter wheels that can give us scientific information about the composition of the rocks, and also give us these RGB color views that would mimic what a human would see if you were standing on the surface of Mars. We also have SuperCam, which is like ChemCam 2.0. Alex mentioned part of this having a Raman spectrometer built into it, but it's also got its laser-induced breakdown spectrometer. So we're shooting lasers at rocks to figure out what the rocks are made out of. And this has been upgraded. So on Curiosity, it had a black and white camera called ChemCam. Now it's got a color camera on this part as well. And we've got an upgrade to the camera at the end of the turret. So on Curiosity, we had the Mars Hand Lens Imager, or MALI, which is the camera that you're used to seeing all of those great selfies with from the rover. Mm-hmm. Yeah. On Perseverance, we have Pixels. So this is designed to both be an X-ray fluorescence spectrometer, which can tell us about the chemical composition of rocks by shooting X-rays at them and seeing what comes back. And it's got this microscopic imager that we can, again, hopefully get these great selfies of the rover as well.
That's and so then cool.
Then we've got, say, a weather station, kind of like we had with Curiosity. So, temperature, humidity, air pressure. And we've got a ground-penetrating radar instrument. And we've sent these to Mars in orbit before. We've got one on Mars Reconnaissance Orbiter and one on Mars Express. But this is the first time we will have sent one to the ground. And this gives you a little bit of information about the structure down to about, I think it's 30 feet below the surface. So we can start to see if maybe there's some buried ice or what that subsurface structure is under the rover.
It's funny because I get so used to the Curiosity instruments and like just like what the palette is and what it can do, and I have to learn a whole new thing now.
Yeah,
like, there's a lot of different capability on this, which is pretty cool. I thought we'd talk about the wheels too. So the wheels got a really big upgrade on this rover. Anthony, our producer, can you bring up the picture of the Curiosity's wheel? You can kind of see what this thing has been facing. So this is what Curiosity had. This is the most recent wheel survey they did.
Oof.
So it's like a couple of weeks ago, and you can see that the rocks are really chewing up these wheels, and those are not cardboard wheels. They're like metal, I don't know, aluminum of some kind of wheels. So they got torn up pretty good. So there's a new version of this, and then we have a comparison picture as well. You can see kind of the upgrades. So you see the left there, that's Curiosity. It's got those kind of zigzag patterns. I guess that made some weak points in the treads. And so now they have these kind of cool sinusoidal ones. And I think they're thicker, they're wider. There's a little bit of titanium coating on them and stuff. So they're way beefier. And I've been assured by all the engineers at JPL that they have been tested more than anything that's ever been tested in your life. They've been driving it in a circle for like 5 years or whatever. So it's been pretty good. So I'm pretty excited about these. And I also wanted to show, we have this really great video of the sample collection technique. So I don't know, Anthony, if you can bring that up. This is we talked about the samples, and it's got this drill that pulls these cores out. That's pretty cool, but it is like a really crazy complicated sort of process. So I thought we'd play this as it's going through here. So yeah, so here's the rover, and you can kind of see, let's see how slow this is, of course.
This is obviously the biggest difference between Curiosity and Perseverance.
Yeah,
is this whole sample catching system.
Totally, it's like the flagship instrument on this thing, right? It's like the most important thing to talk about. So it it goes through it, and it's got an upgraded kind of drill compared to what Curiosity had. Curiosity had some problems with the drill, so I'm sure they've tried to implement some fixes to make sure that doesn't happen again. But it does like a core, and the core is like kind of the size of a Sharpie. I wonder if I have one here somewhere. If you think about something like kind of this size, right? This is roughly what the core of these rocks are going to be looking like. And it has to pull them out of the ground, and then it goes through this like whole rigmarole of stuff to store this. Like there's this sample thing that grabs it, and then it goes in this rotary bit, and then goes underneath, and there's this whole this is crazy underneath here. So you can see there's like this other robotic arm underneath the belly that moves this thing around, and it does a bunch of like analysis and cleaning and stuff that will characterize the sample and figure out what's going on with it, and then it will eventually go and store into one of the tubes. Yeah, look at all this stuff there. Measure volume, seal sample tube. Yeah, tons of stuff that it's going to check there. So like this whole system is just like crazy to me, and this is the instrument that JPL built in-house. They did not really farm this one out, like so Mastcam, for example, is at an ASU, I think, right? And so this is actually one they did at JPL. And then there's the sample tube where it gets stored, and then it gets dumped onto the surface. So that's a crazy system. I don't know. I can't wait to that. If that works, like it's going to be a massive, massive achievement. I don't know what you think about that.
And it's pretty amazing to think that we can do this, 200 million miles away.
Yeah. Do you get like scientist anxiety about stuff like that working once you get?
Oh yeah, for sure. It's so complicated. You're like, there's no way that can work, and then it does because JPL is awesome, and then you're like, okay, they know what they're doing.
I guess if they can do a sky crane, they can probably make that work, right?
Right. Yeah.
Speaking of the sky crane too, one of the things I am super, super jazzed for, Anthony, can you bring up the descent video from Curiosity that we have? So you might remember this footage. This was there's a belly cam on Curiosity that's like the Mars descent imager Marty, and it's like it should be there's a YouTube link in the show notes there, Anthony. Either way, so there's like this belly cam, and it's like only real job to start with was to film, once the heat shield came off, was like to film the descent under parachute and down to the ground. But it was like, it's kind of low resolution. It took a frame every like 4 seconds or something, and there's no sound. But they are like outfitting it. There's like 6 or 7 cameras on the descent stage now. There's a microphone. We're going to get like video and audio. It's going to be just out of this world. I'm just so excited for that. I don't know about you, but here's yeah, you can see the 297 frames. That's all they got for the whole descent. So if you're watching if that was a 60 frame per second video, it would not be very long. But you can see, so that's kind of the resolution you get. And there's the heat shield falling away. Yeah. So this is going to be way better.
There's been some really amazing amateurs that have reprocessed this in like 30 frames per second, like 4K. Yeah. I don't know how they pulled that much detail out of these images, because it's literally like, I don't know, like 640 pixels across or something like that. But kudos to those people, because those versions of the video look amazing.
Yeah, so I guess the nice thing is they don't have to do that this time.
Yeah.
Yeah. All right. Well, speaking of JPL, speaking of these amazing people that do amazing things, we have our next guest coming up here. So Nathan Williams is a science system engineer. He's a geologist, and he has been doing some work on the Mars helicopter. So we're going to bring him on to say hello. Hey, Nathan, how you doing?
Hey, how are you guys?
Good.
Oh, we're so happy to have you. Thanks for joining us.
Glad to
We
join.
know you're on the team, so you are actually like trying to participate in watching this launch, and we're pulling you away 15 minutes before the rocket. So thank you for sharing time with us. Can you give us a high level? Like, what is Ingenuity? What is this Mars helicopter about?
Yeah, so it's the first attempt for us to fly an aerial vehicle on other planets. Simply put, we've flown helicopters, other spacecraft or aircraft here on Earth, and in the high altitudes. But we've never actually tried that on a different planet. And well, I think it's going to be really important for us to actually go ahead and try that out. Make sure that the fundamentals of our understanding for the engineering are applicable not just on Earth, but much more broadly. Additionally, for future missions, this helicopter is rather limited in its capabilities. It's a technology demonstration. Simply, can we do this? But for future missions, an aerial platform could be extremely beneficial. If a rover, for some reason, would have difficulty going to access a site, either it's got too much sand, it would get stuck, or if there's a steep crater wall and you wanted to go see what the layers are at the top of that, but you can't drive up there. Helicopter's great. You just fly up to it.
We kind of had that issue with Curiosity too. There was like the Greenhue pediment, and it was a whole thing to drive up this really steep slope, and we could have easily solved that with something like this.
Yep. So there are other missions being tentatively designed at JPL that would potentially go and examine these in the future. But we want to make sure that we have the fundamentals down first. And this Mars helicopter is the first effort to do that. It's pretty small. It's only 4 pounds, 1.8 kilograms. The entire thing is about 1.2 meters, blade tip to blade tip. So it's really lightweight. It's decent size, but it's still fairly small. And it's got 2 cameras on it. It's got a navigation camera and a much higher resolution color camera that's sort of pointed off to the side. And with the combination of those, we can at least get some pictures back to make sure that it is working and sort of get the perspective that we would expect to see with other future helicopters too.
Sometimes I call that the rover selfie camera.
That is our plan. We actually do plan to take a picture of the rover with the helicopter, and then
We have to, but we'd riot otherwise.
It's not our like highest level requirement, but it's pretty important to us. But in addition to that, there's plans for the Mastcam Z instrument to take video of the helicopter taking off and flying around.
I'm really glad that we got you to say Mastcam Z.
The PI for Mastcam Z, Jim Bell, who's at Arizona State, he was actually my PhD advisor. So I worked on it back in the early days a little bit. So we'll be working and coordinating both on the rover side to image the helicopter, and from the helicopter side to image the rover, coordinating between them for all the operations to make sure that that everything is working as we would expect, to document it as best we can, and make the most out of this technology demonstration. So it's not treated as a full instrument. It's only it doesn't have any higher level requirements that it has to impose upon the rover in terms of it needs to get these specific observations. We do have a month that's going to be dedicated to us doing whatever we need to do for this technology demonstration. But beyond that, there is not yet a solidified plan for what we would do beyond that 30 days of flight.
And this helicopter utilizes a lot of commercial technology. Is that right?
Yes, because it's just a technology demonstration. We can accept a bit higher risk.
Home Depot helicopter.
We bought things pretty much off the shelf. So yeah, we use commercial off the shelf COTS hardware a lot. So one of the things, the cameras, for instance, they're cell phone cameras, like actual cell phone cameras. They're this small. They weigh a gram, and hey, if it works, it works. Totally. We don't necessarily need to engineer it to be lasting for years in a high radiation environment. It just needs to work for that month, and these should be sufficient for that, and it's a lot cheaper.
Totally. Why is it hard to fly on Mars? Like, why have we waited this long to do this?
Well, it's hard just getting anything to Mars, so that's the first challenge, is simply bringing something with you. It's also difficult because Mars is so far away that you can't simply joystick a drone like you could here on Earth. Because by the time that you send a signal, it would take at least several minutes for the light, the communication at the speed of light, just to get there. And then if it's sending signal back, it has to take that same amount of time. So there's many minutes delay of time between when you can actually send and receive signals.
It's
now these
like
flights
those
are only
early
supposed to
drones.
be 90 seconds. Yeah.
Those early drones where you had like the cell phone. Yeah, there was like the early drones, you had like the cell phone, and then like there was like a latency to get the signal up to it when you're trying to fly it, and it was like so frustrating because it was like 2 seconds, but then this is going to be a lot longer than that.
Yeah, so it's
Cool.
that's a challenge. But otherwise, on Mars specifically, it's more complicated because Mars has less gravity. It's about a third of what Earth has. So you think that would help us flying, and it does. Unfortunately, what's hurting us flying is that Mars' atmosphere is only about 1% of the thickness of Earth's in terms of like the number of molecules in it and the atmospheric density. So if you have a lot less air, it's kind of hard to fly. Thankfully, because this helicopter is so lightweight, because Mars' gravity is lower, and because we can spin the blades much faster on Mars, about 10 times as fast as we spin the helicopter blades here on Earth, that is able to generate more lift, and we can actually fly.
That's crazy. It's mind-boggling that we actually get this to work. This is another example of JPL doing something we don't believe can actually work.
And we've been able to test it as best as we can in the lab environment. So we have a vacuum chamber at JPL, and so we can pump it down to only basically Mars pressure is only about 1% of Earth's, and then we can test to see what the lift is in that environment. It's a little bit harder to decrease the Earth's gravity for a test.
Yeah, I've seen those like big springy things, right? That's
exactly. So we do put it on a spring, and that applies an acceleration to it to counterbalance the gravity. So we get a rough idea, and it does fly in those tests in the vacuum chamber. But we want to make sure we can actually do it in the real world and from literally millions of miles away.
So they're showing a video here. This is like the deployment sequence.
Yep.
Is there anything about the helicopter or monitoring the flight path or anything like that that will teach us about the atmosphere of Mars? Yeah,
I mean, we have some weather measurements from basically 2 meters above the surface, or even a meter, depending on which instrument we send in the past. Those are fixed. The helicopter can fly a bit higher up, so we can understand the boundary layer effects of the atmosphere a little bit better. Because if you're near the surface, if there's rocks or other rough terrain, the wind sort of gets hung up on it. It has a drag effect. And if you're higher up, that may be a bit different, and that can act differently in the lower Mars pressure as well. So we can learn about that. Hopefully, when we're flying the helicopter, and we're going to be looking at the weather data from 2020 Perseverance as well, we'll be flying in relatively calm times of day, so it hopefully won't be too bad. But we'll still learn a bit about how it is to fly that, and how it is to simply, like, do we have drift in the helicopter itself because of higher level winds that we didn't expect? We'll find out.
Hopefully not too much drift.
Yeah. So this is a technology demonstration, like you said. So I guess we should probably level set. Right, there's a very good chance this could not work, or it could crash, or it could perform very differently than we expect. Can you just maybe give us some grounding? Like what should we expect from an overall tech demo like this?
So yeah, I mean, anything can go wrong. We're going to try our best to make sure that it works successfully, and we have been doing a number of tests already to do that. And make sure that we pick a good terrain for it. We plan to do at least 3, ideally 5 tests within the first 30 days of dropping it off, which should be about 2 to 3 months in, whenever we find a safe site to drop it off. And these flights are going to start out simple. It's just like go up 2 meters, drop back down, go up 5 meters, maybe go over a little bit and then back and then drop back down. And then the main nominal flight is to go up over 50 meters, so like 150 feet, and then back to the original spot and down again. Future flights, we can send it farther. It could go potentially up to 200 or 300 meters if we just say go in this one direction and don't come back. We can send it that way too. But we haven't committed to that yet. Like, first things first, fly.
Well, Nathan, thanks so much for sharing this with us. This is so cool. I'm jazzed for the helicopter. I hope that this is like the Sojourner of powered flight, and that this is like sets a course for us for lots of cool aerial exploration. I know you have to go because we're getting close to launch. We're about 5 minutes away, and you are, this is your spacecraft. So I'm going to let you go. You can get back to your team, and good luck today. Thanks for joining us.
Yeah, thanks, and have a happy launch day.
You too.
Bye.
Good to get the stream up there. So we're 4.5 minutes away. This is it, Tanya. We're here.
This is so exciting.
Yes, it's funny talking to him like that. You've told me your story. We did a whole episode about Sojourner and Pathfinder and how inspirational Sojourner was to you as a little tech demo. Tech demo rover thing that was not part of the main mission. I just sometimes I think about, like, what is Ingenuity going to do? Who's the next Tanya of Mars that's going to be inspired by this little helicopter to explore Mars for their career, right?
Yeah, that's what I'm hoping. Some kid is going to see that flying, and I mean, we've never done anything like this before on another planet. So I really hope that just blows someone's mind and they get enamored with Mars and start to go down this path.
Totally. Yeah. All right, so we're going to bring the stream up to the main screen here and get our mugs out of the way. So we're about 4 minutes in. We've got a go for launch, which is very exciting. Looks like we got some venting going on, and so we're just going to sort of listen in for these last few minutes, have a few comments, but we're going to just kind of enjoy the launch. So thanks everyone for joining so far. Don't go away after the launch though, because we have more content coming up. We're going to talk a bit about the launch itself. We're going to talk about what's going to happen next and all that kind of thing. But then we have a third guest coming on, Phillip Hargrove, who's from NASA Launch Services, and he's going to tell us about trajectory design and kind of how we get the spacecraft to the place it needs to go. So that's going to be really exciting. So don't go away. We're gonna be here all the way until spacecraft separation.
Kind of preview for you what's going to happen, because there's going to be a lot going on. You're not going to hear much from us. You'll actually be hearing from the ULA flight commentator Jesse Gonzalez. He'll be kind of giving those calls.
I love the frost. It's like piping ready to go.
Yeah.
Separation, and then fairing separation.
The sky looks great.
And then
yeah, it does.
The first main engine ignition of the Centaur,
yes.
RL-10. And so then you'll kind of hear us jump back in and help provide some more context to what's going on. We encourage you to stay with us for
I'm glad the weather turned out, because there's that big storm coming in too, right?
And we are far from over.
Yeah, I'm not sure how it's going to affect the crew return on the weekend, but at least it looks good for Percy.
February, when Mars 2020 safely delivers Perseverance and Ingenuity to the surface of the red planet. So we're going to let you listen in now and enjoy the last couple minutes of the process of launching a rocket.
2 minutes.
1 minute.
Yeah,
59.
weather looks great.
Vehicle internal.
1 minute.
Don't see any
55.
wayward boats out there.
Sequencer start.
1 minute 50.
Securing Centaur LH2.
Securing Centaur LO2.
Tori Bruno says that we should
1 minute
be
40.
Yep,
we should
fueling is
watch
on.
very carefully, because
Team is
4
going.
solid rockets, this
Team
thing's
is
going to leap off the pad.
Sequence is ready to go. They're getting ready to turn the vehicle over to auto sequence at T-minus 31 seconds. So that's a big thing that they're getting done here. At T-minus 25 seconds, we will hear the team give their final goes that everything is ready and
1
the
minute
launch
20.
vehicle is ready to lift off and perform this mission.
SCS count
1
started.
minute
Oh my
15.
God.
Produce CSCS for launch. Roger.
1 minute 10.
Vent valves locked.
Oh, man, is this happening? Right on schedule?
1 minute.
Rock, report
I
range
think we're going to do
status.
this.
Range green.
That's good to hear, Joshua, right
That means
there.
public safety there is accounted for, the FTS system. There you see on your screen a beautiful shot. The skies look great. There is little wind happening. You'd be able to see more of the venting. If there were wind, the trail of that venting. So we're ready to go.
And actually, that's an
40
important
seconds.
point. The reason we don't see that
Stable at
venting is
step
the
3.
vent valves have been locked up to put flight pressure into the tanks. And as we just heard, they're stable at step 3, which means the tanks are ready to go. And here at about 5 seconds. We will
28
hear
seconds.
the team
ECS reduced for launch.
give their
Roger.
final go.
25 seconds.
Status check. Go Atlas. Go Centaur. Go
Woo!
Mars 2020.
Go,
There we go.
Percy.
We're ready to go lift off this morning, Joshua.
Eight, 7,
All right, Tanya,
6,
let's do it.
5,
5,
4. Engine ignition. 2, 1, 0.
Ah!
Release.
We're going to Mars!
Liftoff. As the countdown to Mars continues, the Perseverance of humanity launching the next generation
Wow,
of
Tori
robotic
was not
explorers
kidding. Look
to
at
the
that
Red
move.
Planet.
Yeah, it's gone, man. It is out of there.
It's like Sea Earth. I'm out of here.
And Atlas
No
TU
pandemic on
closed loop
Mars.
Control.
Wow. This never gets old.
It never does.
Coming up on 30 seconds into flight, the RD-180 is throttling down as expected. Engine response looks good.
They're already throttling down. Holy shit.
And Mach 1 Atlas 5 is now supersonic.
Yeah, compared to the last few Falcon flights, this is just like cruising. Wow.
Or like when you see one of those Atlas 401s.
And passing 45
Yeah.
Just, like,
seconds
hover
into
off
flight,
the
vehicle
pad.
is now passing
Like,
through
is that even going to
Mach
make it to
2
orbit?
maximum dynamic pressure.
Oh, wow. It looks great.
Whoa.
Early morning sunshine in the clouds or the smokestack.
And passing 1 minute into flight, the RD-180 is throttling back up as expected. Engine response looks good. At this time in flight, the SRB chamber pressures remain nominal. The RD-180 pump speed and fuel injector pressures are responding well to demands on the engine. Standing by for SRB burnout shortly.
Good infrared tracking shot there.
That's beautiful.
And we have burnout on all 4 SRBs. Burnout pressure signatures look good. Standing by for SRB jettison shortly.
All right. Those Aerojet side boosters have done their job. Off they go.
And we have a good indication of SRB jettison of all 4 SRBs. And the vehicle has gone to closed loop guidance. Vehicle body rates are responding nominally at this time.
Okay. So let's see. What's trying to think what our timeline is here too. I'm gonna bring up my old. Let's see.
And coming up on 2.5 minutes into flight, the RD-180 is throttled down slightly as expected. Engine response continues to look good. At this time, the vehicle is 50 miles in altitude, 85 miles downrange, traveling at 6,000 miles per hour.
So the main engine cutoff is like plus 420. So we got about 2
And the
minutes.
Centaur
or so,
reaction control
minute and a half
system is now
left of
pressurizing to flight
core
levels.
stage. Fairing in about 30 seconds here. Oh, that's a weird shot. That looks hazy. What is that?
And just past 3
I don't
minutes
think
into
it
flight,
is.
the RD-180 is now throttling to maintain a constant 2.5 G acceleration limit for payload fairing jettison. Engine response and vehicle acceleration look good.
You mentioned frost earlier. That's pretty frosty.
Yeah.
Woo,
There
there
go
it
the
goes.
fairings.
And we have
Big
good
old
indication
fairings.
of payload fairing jettison and Centaur forward load reactor deck jettison.
Tori did a great little outreach thing on Twitter about the fairings and how this is a small payload for such a big
And
rocket,
the
and so they
RD-180
had to use.
is throttling back up to attain a 4.6 G acceleration. Engine
had to use
response continues to look good.
the big fairings because it adds structural support to it, and because Centaur just like wouldn't have been able to handle the loads without
And
without
Centaur
it.
has begun the boost phase chill down sequence to thermally condition the RL-10 for operation. Standing by for BECO shortly.
BECO.
BECO is
I always forget they call it BECO.
Yeah.
BECO's the call for booster engine.
And we have BECO, booster engine cutoff, standing by
Yeah, it's
for
no
stage
good, right,
separation.
Anthony? What was that about? There she goes.
And we have
Thank
good
you,
indication
Atlas.
of Atlas Centaur separation.
You did good.
So there you're seeing live footage.
And we
from
have
the
MES
rocket.
1. RL10 operating parameters look good. Chamber pressures are stable.
Oh, I like you can see the nozzle moving. That's great.
Yeah.
All of this just is a great reminder of how complex it is
This
to
will be the
get
first of
something
2
into
burns
space.
for today's mission. This
So
first
much,
burn
yeah.
will be approximately 7 minutes in length.
All right. Yeah. This is the long burn. First one. So it's gonna go. This is gonna burn and put it into a parking orbit, and so then
Mick,
it'll
that's
be
pretty
just
exceptional
kind of
footage there.
around
That's
Earth.
live video. We will see that switch over shortly into an animation that kind of helps let us know what's happening with the rocket. But right there, a beautiful liftoff. Fun to feel that rumble in the building here as we proceed towards orbit and then towards Mars destination.
Yeah, absolutely. It was great watching an on-time liftoff of the Atlas V with that little over 2 million
Great
pounds
on
of
time.
thrust. Cleared the tower in roughly 5 seconds. Josh, you and I worked the InSight mission, and if you recall, that mission on the West Coast took about 17 seconds to get past tower. So with those 4 solids today, this thing really got out of here and on its way. And it's,
That's a great
as we hear
comparison.
from Jesse,
Yeah.
everything's looking nominal, and all vehicle parameters are within the design limits, and we're getting ready.
And
to come up
InSight
on
was a
main
light
engine
payload
start for
too,
that
so
first burn that Jesse was talking about.
Yeah, so recapping this countdown
if they had
to
a
Mars,
401 with like
the
a big
stations
payload,
began
it would
to
be even
filled up this
slower,
morning
right?
just after midnight. Preparations, fuelings, powering up, all the way through that liftoff that happened. I think, Mick, it wasn't precisely on time. I think you said it was like 10 milliseconds early. So it's pretty much dead on.
Yeah, dead on. This team does a great job. As I said, they're very focused, very disciplined. As Tori also said, courageous. They have done a lot of work to get us to this point today through this pandemic, changed how they did some of their work.
Cool.
Made adjustments.
So yeah, we're going into our burn here. So like I said, it's going to go into a parking orbit. It's going to hang out on Earth for a bit. It's got to go around to the other side. I think I have a map. Actually, Anthony, could we bring up the trajectory or sort of the flight profile? There's a picture of like the launch sequence.
Yeah, we had a really quiet
And we can
countdown
see there's like a
today,
little
which is
map on
phenomenal,
there,
that we got off the ground
which is
on
really
time.
good.
And we are proceeding now that we are in the middle of the first burn. It's tough to
There
make
we
out,
go.
but that engine is lit.
Hopefully you guys
It's
can read
firing.
that.
So we have motion. There you
But
go.
so we're over in Florida there. So if you head down to the map, yeah, so you can see Florida there. And then if we get all the way around
The space tracking
to
system,
so number 7 is where the second engine cutoff is. So we're in between 6 and 7 right now. And then it's going to coast all the way to 8, which is over here in the southern Indian Ocean, and then it's going to burn again and go off to Mars. And that's the whole trans-Mars injection sequence there. So we're going to basically go around the world before we're going to do anything there. Tanya, how was that? Did you enjoy that?
That was amazing. Almost as good as being there in person.
Almost as good. Almost as good. I miss the reverberation in your chest when those solids are really kicking, right? Actually, I haven't seen a solid rocket booster. Everything I've seen has all been liquid, and apparently solids are just like they thump you real good. That's what I really want to see.
Next time.
Next time, yeah. But this is the last Atlas to launch a Mars mission, though. Did you ever think about that?
Oof, no. I'm gonna get all teary-eyed now.
It's launched 8 missions so far. This is the 9th. But there are no Mars missions for the United States on the books before Vulcan takes over and Atlas gets retired. And so
Oh wow.
this is it. This is the end of the Atlas Mars heritage today. We just watched it.
Well, now
How's
I'm
that
even
for a
more
sad
sad
tea?
to not be there in person. Oh,
I feel like nobody's talking about that. I don't think they want to bring that one up too much yet.
end of an era for sure.
Yeah, so I guess that means the second flight of Mars sample return, which is the lander and the fetch rover, that would be on Vulcan. I think that's the U.S. is launching that one.
Yeah.
Yeah. Well, Vulcan's gonna be pretty cool too. So hopefully that's good to go.
Yeah.
So we have some time left before our next guest. So Phillip is actually he's in Florida, so because he's with Launch Services, he wanted to actually go and watch this thing go up. So he's presumably running back to his car right now and trying to get back to his apartment to hang out with us. So we're going to talk a little bit before we do that. I thought we would take this opportunity to talk a little bit about some of the work that we do on the side. So Tanya, I don't know, do you want to talk about your book? Because you have this fantastic book that you wrote and that I'm lucky to have here, and it's pretty cool. You want to tell us about it?
Sure. It's surprisingly not about Mars, which I think threw everybody off for my first book. But I also love the moon. And I had been interested in hearing the stories from people that watched or listened to the moon landing live as it happened, but from outside the United States. Because whenever we hear about Apollo, we get to hear this very, well, at least in America, we hear this very patriotic version of it, or sort of the space race, America versus Russia sort of thing. And I wanted to know what was the international perspective, because when Buzz and Neil went to the moon, they left a plaque there that said, "We came in peace for all mankind." So I wanted to know what that feeling was like for people around the world. And I interviewed folks, 8 different people from pretty much every continent except Australia and Antarctica, to ask what their perceptions were at the time, and then what they think about how the space program has progressed between Apollo and now, and what they hoped for the future. And the stories range pretty widely, everything from a woman who was 5 years old in rural northeastern India at the time of the launch, to a 44-year-old Holocaust survivor who was working as an engineer in Canada after the war. And he was greatly inspired by this. And I really wanted to talk to people that were also not necessarily space people, because that's a story you hear all the time. I saw Apollo, I was inspired, and then I ended up working at JPL, or I became a professor. But what was this like for somebody that was a school teacher, or just a random person in the world? And the messages from everybody were pretty consistent in terms of feeling like this was a human achievement, not just an American achievement. They saw this as something that really was the future of humanity. And that was really beautiful to hear. So if you're interested in hearing stories from people around the world, definitely check it out. It's called For All Humankind. We updated the language a little bit for the 21st century.
No, it's great. Yeah. And you wrote this with Danny Bednar, who's a pretty cool guy, right? I think I don't know if I've met him, but
I think I guess he's pretty cool. Yeah.
Yeah.
He's a professor at the University of Western Ontario. We did our PhDs there together, and now he works in policy for the Canadian Space Agency.
Nice, cool. Yeah, so you should definitely pick it up, Martian. So For All Mankind, it's a pretty cool book.
For All Humankind.
Sorry, For All Humankind. Wow. It is still early in the morning here. I'm going to give myself that.
Okay.
It's got this lovely, cute animation on the front here too. This illustration, I love it. So cool. That's great.
Thanks.
We'll do more plugs as well. So if you like this live stream, of course, I have to take the opportunity to do some shameless self-promotion. Of course, we have a Patreon that helps me do these things. So if you go to WeMartians.com/support, you can be a patron of this show as well. It's real easy. It's like a couple dollars a month, basically whatever you want to pay, and you can get some different perks of it. The level I like to really market is the $5 level. So $5 a month, which is less than I spend on coffee, although not today. You get access to a Red Planet Review, which is like a weekly news podcast for Mars. I go over it every Friday. There's a little bit update, 10-minute podcast about all the different news that hits your feed. You get access to our Discord community, which I have to say is like the best place to hang out on the internet. We have this private Discord. It's small. It's very intimate. Everyone kind of knows each other. There's been just a ton of really great conversations about there. They're hanging out here in our live chat, kind of hanging out with us and throwing comments at us, and they're really experiencing this all together, which is really fun. I share that Discord with my partner, Anthony Colangelo, who's behind the scenes producing today. And his podcast listeners are in there together, and we all kind of share and hang out. It's just awesome. So you get to hang out in there with us. And then you also get access to early interviews as well. So when I do things like this, you get advance notice. When I bring guests on the show, you get advance notice, and you can submit questions, which I do ask on the show. Try and credit you when I remember and it's appropriate. And so that's really cool. And it's just cool to hang out. So I want to do this full time, and I need support to do that. So I really appreciate you do that. So WeMartians.com/support. And then I appreciate that. And for all of you who are already supporting, thank you. This is really fun to do this, and I want to keep doing it. Okay, so that's over with. I hate selling myself. I don't like doing it. I also want to bring on our producer Anthony a little bit. Anthony, can you turn your video on and join us for a second? Hey,
Hello.
Anthony.
Good morning.
Thanks for doing all this for us. We really appreciate it.
This has been fun. It's more hectic than I was ready for. Like, I was mentally prepared. We've done the Off-Nominal streams before. But now I've got like 8 different, of course, Jake is the planner of our space partnership here. So I've got PDFs everywhere. I've got schedules to go off of. I'm flipping through stuff, but it's been a lot of fun. And I know I saw a lot of comments in the chat that your stream is much more fun and engaging than others out there. So I personally have learned a lot, like listening to the sign. I usually just get this all from Jake, but now I can get it from Tanya and everyone else that's been on so far. So this has been fun.
I sent you a message in our chat and I was like, this schedule is fast. I made this fast. I didn't think I really realized how fast this was. It was just like bam, bam, bam through the guests. I wanted you to have a chance to talk about your podcast too, because you do great work with space content. Can you tell us a little bit about Miko?
Thank you. Yeah, it's called Main Engine Cutoff as opposed to Booster Engine Cutoff that we had today. Actually, we've got 2 Mikos on this launch here because they call Centaur's engine. I've got my Centaur shirt on today. They call that the main engine on Atlas V and Centaur, so that's been fun. But yeah, we talk mostly about rockets and politics and business over there. MainEngineCutoff.com. Not a ton of the science side. I leave that to you and the experts. But it's if you care about policy or business or strategy or launch vehicles. Honestly, I'm big into launch vehicles, and it's a good time right now. I'm thinking we're about to get some big news on the launch vehicle front. I've heard this week or next that we're going to hear from the Air Force round of funding. So head over there if you want to check out some of that stuff, if you're into that sort of thing. Or right here on Off-Nominal. We've been doing a lot of Off-Nominal streams lately. So that's been a lot of fun.
Off-Nominals are our shared podcast that we do together. It's our casual space. It's where we hang out and experiment with stuff like this. And I have to say that I think experimenting in Off-Nominal videos kind of helped us do what we're doing today. So it's maybe it's actually bearing some fruit.
Yeah, totally. Right.
And I want to plug an episode as well because we've got our next guest, Phillip Hargrove, is on in roughly 10 minutes or so, and you actually had a full interview with him, and so that came out yesterday, the day before, like just the last couple of days.
Yeah, we talked on Tuesday, and we talked a lot about Mars 2020 in there, but also about NASA Launch Services Program generally, about what kind of work they do, the way that they interface. They sit at this interesting spot, as I'm sure we'll talk about here, that they're between the science teams and the NASA teams and the launch vehicle providers. And they are the point at which all that comes together. So they've got a lot of analysis that goes into the science teams needing to know what kind of thermal conditions they're going to see en route to wherever they're going, the loads that they can take from the launch vehicles. They need to talk to the launch providers about what the science team needs and what the mission team needs. And it's kind of the galaxy brain of all these programs. So it was awesome to hang out with him. And we also got into my little pet thing that I'm interested in lately is these new polar trajectories out of Cape Canaveral that SpaceX is bringing back pretty soon. So they've got a commercial launch coming up next month or so that's going to go polar from Cape Canaveral, but SpaceX also recently won the PACE mission that's going to do the same in, I think it's like 2023 or something like that. So NASA Launch Services is following along with these kind of providers to get the data out of these launches so that when it comes to launches like Perseverance, they have all the data they need to say that, the Atlas V 541 is the right choice for this mission.
Cool. And then maybe we will plug our recent Off-Nominal episode too. Tanya, you did Off-Nominal way back in the day.
I did.
You can espouse it's great fun and joy, right? It's real fun.
It was. I'm trying to remember. We came up with the acronym Flamingo, but I cannot remember what it stood for. Like
flying around Mars. Ooh, I don't know.
Imaging something.
Yeah, these are the shenanigans that we get up to on Off-Nominal.
You neglected to mention that Off-Nominal involves booze. Like, this is your number one selling point. Come on, guys.
It does, yes.
For us, anyway, yeah.
So I like to show this is my mouse pad, and there's the logo for it, and it has a rocket beer bottle. So that's how you know it's fun. And so we actually recently had Richard Garriott on. So if you don't know Richard Garriott, he's an entrepreneur. He is a video game developer. So if you are into like role-playing games, you will know him because he invented Ultima. Like it's like foundational level role-playing games on the computer. So and so he did that for a long time, made a bunch of money, and then said, hey, you know what I'm going to do with this money? I'm going to go to space. And went to the ISS on a private mission, and this is so the kind of guy who can buy his way to space has an endless font of stories to tell. And we had so much fun hanging out with him and learning some stuff. So you should check that out. It's a video and an audio podcast. You can do whatever one you want. I like the video because you can see his crazy drink that had like,
oh, that was sounded good though.
Coming out of it and stuff.
That sounded really good.
It did sound good, yeah. He's in Paris and he's very fancy Parisian. He's like, oh, we just get this down.
He's in Paris, but he was also inside a shed in his backyard when he did the show. So he was keeping it exactly off-nominal. Like that was my favorite part is that he had, like, there's some people that come on that just were like, oh, this person already, we don't have to convince them that they're going to have fun with us. Sometimes people are like, okay, I don't really know what's going on here, you know? And he signed on and I was like, oh, he's already got it. He's in a shed with a drink and he's ready to talk about, going to the
This can be the
Titanic
episode. This can be the episode that you send to future potential guests. Like, if you want to know what to expect, here you go. Like, you need to at least meet this level.
A millionaire in Paris in a shed drinking a fancy drink who bought his way to space and to the Titanic. Yeah.
Anyways, yeah, so you should check that out. It was a lot of fun. We do lots of fun stuff on Off-Nominal. So Anthony, thanks for sharing all that stuff with us. And thanks for producing. This has been really fun. This is like, it's so much nicer to not have to worry about all this stuff and just let the guy behind the curtain do it.
Well, I'm glad. I will let you get back to the stream. It looks like we've got some stuff coming up here pretty soon. So thank you again.
Yeah.
And enjoy the rest of the stream, everybody.
Thank you.
Thanks, Anthony.
All right. So it looks like the Centaur has ended its burn. Now it's coasting. Look at that thing just soaring around there. So you can see there's the upper stage there, and then the spacecraft on the, well, it's upside down right now, but spacecraft on the bottom.
Yeah. It is pointed in the correct direction. Don't worry, people.
Yeah, that's correct. Yeah. It's such a little tiny cruise stage. Hey, I always forget about what it looks like. I mean, Anthony, can we find a picture of the cruise stage with the spacecraft and all buttoned up? Because this is always kind of, sometimes you think of like spacecraft as like, having these big solar panels and this big like gangly thing because it's space, but this is like a nice tight little package. And I guess it's because they can probably use I'm spitballing now, but they can probably use the RTG on the cruise stage too, right? They don't need to wait till they get to the surface to use it. What do you think?
I don't see why they couldn't. I don't know if they do, but I don't see why they couldn't do that.
I know there are like some little solar panels on the side of the cruise stage. Yeah, so that's the heat shield. Yeah, that's pretty good. So there's a heat shield that's facing us, that dark spot. The spacecraft's inside there. And then that little white ring underneath it, that's the cruise stage. It's basically like a disc. And I think one side of it has solar panels. Those kind of like white side panels there are the non-solar side, or maybe they're not on yet. I can't tell, but they're just like, yeah, it's real simple. So I don't know, that's always kind of like, I remember when I first learned about that, I was like, well, that's kind of an interesting package. I don't know. That's my thoughts on the cruise stage.
It's very neat and contained. Like once you see what actually goes to Mars versus all the stuff that went off the launch pad to begin with. Yeah, I mean, this is basically all you're left with at the end. It's pretty impressive.
Yeah, totally. Yeah, and so there's, you can see it a lot better there. The exploded view, the unfortunate name for engineering diagrams on spacecraft. You never want to call a spacecraft exploded, but you can see the in the top left there, those black panels all the way around. That's kind of where the solar panels are. So it's very small.
I guess one thing that we, while we wait for the next guest, one thing we didn't really talk about was the terrain relative navigation aspect of the sky crane and the landing on this. And that's pretty cool because, before we've just kind of had to land wherever we happen to be coming down. And now we actually can use all of those cameras that you mentioned before to check before we land, are we actually coming down over a big pointy rock that we really don't want to have the rover come down on? So we can move around laterally to make sure we're landing in the ideal spot.
Yeah, it's crazy. So they actually take pictures as they're flying to the surface, compare them to maps, and then adjust as they once it figures out where it is, they can adjust as they need. It's crazy. And a good illustration of that. So the Chinese rover that launched a week ago, they come up with these landing ellipses that are basically like, it's like an oval shape that's like, this is roughly where we're going to land, and it's squatter and long because you're coming in from one direction, so your uncertainty is bigger in one direction than it is side to side, right? So you have these big long landing ellipses, and the bigger it is, the less accurate you are. So the Tianwen-1 Chinese rover, its ellipse is like 100 kilometers long. It's like really, really big because there's like, we don't really know. We don't have a ton of control. We're just going to kind of aim for the middle and hope for the best. but Perseverance gets that 100 kilometers down to 13. So, basically 10 times as accurate as they would be. And I think even Curiosity was not like that. Curiosity didn't have terrain relative navigation. So I think it's, I don't know, maybe 20 kilometers. I can't remember now.
Somewhere around there, yeah.
Yeah.
And that's what's enabled us to be able to land inside of these craters. We wouldn't have tried to do something like that with an airbag landing system like we had with Spirit or Opportunity. And it just shows the wonderful upgrades that we've made in our ability and the things that we've learned from missions that we applied to the next ones, like improving the wheels so they don't get quite so crunchy on Perseverance. But, that was something we couldn't have expected either. Gale was way, way crunchier than we would have anticipated.
There we go. There's some landing ellipses. So there's the yellow one at the top where that's Jezero. That's where we decided. The blue one is Northeast Surdist, I think, which is the other candidate that didn't get picked. But you can see, so it's longer. And actually, the more accurate you get, the more it approaches a circle, I guess. So it's less elongated because of Jezero. Actually, and you mentioned too, because learning from Curiosity, Jezero was actually a candidate landing site for Curiosity. And it was eliminated because they couldn't land accurately enough for it to be safe. And so it got punted to the next mission, kind of. But
yeah, and it's almost a consolation because the top 2 landing sites for Curiosity were Gale and then Eberswald, which was a delta inside of a crater. And when we were so enamored with Eberswald, a lot of that was before we had discovered Jezero. And Jezero is actually probably a much more interesting delta site. So it's almost good that we went to Gale with Curiosity, and now we're going to this new delta with Perseverance, because it gives us a different environment with a much more diverse mineralogy in that delta structure than we would have had if we had gone to Eberswald.
So you're a geomorphologist. Is that a fair characterization? So are you
right.
super stoked about the delta, just from a sedimentary kind of perspective?
Yeah, I think it's going to be really cool once we finally get up to it and start taking a look, because we haven't looked at anything like that from the ground on Mars. And obviously, well, at least to a geologist, Jezero from orbit looks amazing. And it's really cool morphologically. It's really cool mineralogically. So I just want to start, going through and sampling all of that and see what's there. And that was definitely back when I was on the team for Perseverance before I left to work for Planet. I was on the landing site working group advocating for Jezero as a landing site. And then for Curiosity, I was on the Gale advocate team. So I'm 2 for 2, which feels really good, even though, I play a very small role in just doing some science to be hey, this site is really cool. We should go here. But it feels pretty good to know that you have picked the sites that the scientists agree are hopefully the most interesting for us to go to.
Totally. Yeah. Sometimes I think that the search for life is so important, and we're getting samples, we're looking for life, we're flying a helicopter, all those things get kind of front and center with the mission. Sometimes we just forget that there's just straight up some cool geology to do in Jezero, and I can't wait for that. So it looks like we might have Phillip pretty soon here. We're seeing him connect pretty way here, so we'll be able to talk to him real quickly here. You made good time. That's pretty good. What is it? So it's T+28. He'd be able to get back from the launch site wherever he was watching from. Was pretty great. Anthony, how we doing? Is Phillip ready for us? Phillip, if you're listening, we don't have video for you yet, but we're close. It feels close. And I see that booster is still kind of just tumbling through its orbit right now. This is sort of that slow, it just uses the natural turn of the Earth to turn itself around. It's really clever. What do we have? T+28. So we have main engine starts T+45. So we have about 17 minutes left before the Centaur is going to turn on again. And then that will be the Trans-Mars injection. And so in that time, we are going to have a great conversation with Phillip. Phillip, can you hear us? Yeah. Hey, there you are. Yeah. How you doing, man?
Good. Man, I'm pumped. I'm kind of speechless. That was awesome. It was really great.
Yeah, we need a report from the ground. What was it like watching that rocket go up?
Okay, well, so I decided not to go all the way on to center because it's that might have been a little too risky to try to get off. So I just went to this place that's right across the Indian River in Titusville, which means that I was directly west of the launch pad, which means that I was looking directly east. It's 8 a.m, so I was looking right at the sun. So that was a little rough, but it was awesome. We were, scanning and, trying to find the pad, and then it just it lit up, saw this bright light, and that thing was going. Those solids really get it off the pad quick. So
they do, yeah. We were just talking about how fast it goes up compared to some of the other rockets we see.
Yeah, that was just incredible. I normally take time lapses of the launch, and I got one of this one, and it was 10-second time lapse. That thing was off and going really fast.
Yeah, Tori Bruno on the live stream was like, don't blink when we say ignition because it's gonna go real fast, right?
Not lying.
So we're super excited to have you with us today. Thanks for rushing back to hang out with us. We really, really appreciate it. So we're waiting for the second Centaur burn right now. Everything looks like it's good to go. We wanted to talk a bit about trajectories and stuff. And you're with NASA Launch Services. Can you maybe just give us a high level? What is NASA LSP and what kind of work do you do?
Sure. So Launch Services program is based here at Kennedy Space Center, and we are a big group of people who really helps make what happened today happen, or well, I guess what's continuing to happen today happen. So when NASA, has a big science mission that they're putting together, they have spacecraft, that can be several years, even decades of development, and then at some point they get to a point where they're ready to procure a launch vehicle and get ready to work towards launch. So when they do that, they come to us and we facilitate that process. We actually evaluate the proposals that we receive from the launch service providers, and we figure out which rocket is the best fit for a given mission. So we evaluate it on the technical side, and we looked at, and this is all under the umbrella of a contract called NASA Launch Services 2. It's a NLS2 contract. So there's, the providers that are able to bid for any of our missions under that contract. So we figure out which one is best from the perspective of, performance and cost, and, what we really want to do is just maximize access to space and minimize the risk. So throughout those few years prior to launch, we work closely with the spacecraft team and the launch vehicle team to really put all the pieces together, physically and, in terms of just preparation. So I'm in the analysis group, where we just do all of the math to, make sure that things are as they're supposed to be. So I work on the trajectories, as you said. So we model the trajectory. We make sure all the requirements are consistent. We make sure that they make sense and that they're really going to put the spacecraft where it's supposed to go at the right time, go in the right speed and the right direction. So it's a lot of interesting work.
So you're basically just a rocket buyer.
Yep. We buy rockets and not to minimize everything you just said, but it's that's a cool way for me to think about it. It's I buy rockets for a living, no big deal. Exactly.
So can you maybe walk us through how do you begin to plan a trajectory to go to Mars? How can you just tell us where you start with them like that?
Yeah, so it's interesting because I actually teach an orbit mechanics class. So you're getting some free lessons here. This is the stuff I was talking with my students about just a few weeks ago. Because there's a problem in orbit mechanics. There's a sort of a mathematical formulation called Lambert's problem, and it's basically the situation of if you have two planets, where they are throughout time, their position and their velocity, you can fairly easily figure out how much speed or how much energy it's going to take to get from one to the other as a function of when you leave the first one and when you want to arrive at the second one. So this may be a good time to pull up. I sent Anthony the pork chop plot for this mission. I don't know if you have that. Pull it up.
It's a great name for a plot.
Yeah, it's great.
Yeah, that's definitely one of the fun ones. Is it up already?
Yeah, we can see it. Yeah.
Okay, so I'm kind of working off the memory here because I can't see it myself, but you can maybe imagine just by looking at the plot why it's called a pork chop plot, just because of that sort of weird kind of extended egg shape. So basically what this is looking at launch dates and arrival dates, and all of those contours that you're seeing are contours indicating how much energy it's going to take to get from Earth to Mars based on those launch and arrival dates. So we figure out the intersection of that plot with the performance of our vehicle. So obviously you want to have the most efficient path. You want to minimize the amount of energy you need to get in between, or the amount of energy the amount of energy that it takes you to get from Earth to Mars, so you can get a less expensive launch vehicle. You could just, kind of blow it out, get the biggest
Right,
vehicle as fast as possible. But you want to be efficient. So you find that intersection of the performance that you need based on the vehicle capability and based on the spacecraft mass that you have. So you look at one of these plots that are generated by, like these are sort of, fixed pieces of data that you can really just pull up, and you figure out what dates work for you, and then you design your trajectory around that. So that's sort of the top level. And then once we start working with them, really the people at JPL, they get into all of the really, really deep details on when exactly you need to tweak your trajectory. During the coasts, they have their planned trajectory correction maneuvers. One interesting thing, and then I'll stop talking, is that they actually, they bias the launch injection to actually miss Mars for the sake of planetary protection. So even if you, hit perfectly nominally and went exactly where we told the launch vehicle to go, you would miss Mars by a little bit. So, now I can see the pork chop plot. So the spacecraft actually tweaks itself on the way to end up getting to Mars.
Right.
Interesting.
So then basically like the middle of that plot is like the most efficient spot. And then as you go out, it takes more and more energy is kind of how to interpret it, right?
Yeah. So if you imagine this being like one of those like topography maps where you're looking at a hill. So, and I guess this is a valley, not a hill. So that the center one, the center blue, sort of egg looking shape or bean looking shape, that's the lowest point. So you want your launch period to be somewhere in there, because if you look at those lines, you see I think the number 15 or 20 at that one. So that's that's a measure of C3. That's a measure of the energy that it's taking to get there. So you want to be somewhere in there. And then all these other shadings are some of the other things that come into play. And I mean, this stuff is really interesting when you look at it. I mean, on the right side of the plot, you see end of dust storm season, because they're saying, hey, we don't want to arrive at Mars in the middle of dust storm season when the whole planet is shrouded, right? And then the orange and the purple shading, that is when they're getting communication from either the Mars Reconnaissance Orbiter or DTE is direct to Earth communication. So they want to have redundant communication for those 7 minutes of terror. I don't know if y'all talked about that at all, but the entry, descent, landing scenario, when it takes 7 minutes to get to the ground and it takes all that time for the data to get back to Earth. So they want to be able to communicate the entire time. So those are all the things that they look at early, and then, crunch the numbers and send us targets, and the launch vehicle makes it happen.
I'm like obsessed with this plot now. I'm just staring at it and trying to
There's so much information in there.
There's so much to read on this. And so maybe this might actually be answering my next question. But one of the things that we get asked a lot is, how can you hit the exact same landing date with Perseverance no matter when you launch? And so I know you guys calculate trajectories for like every 5 minutes in the window and then like every day in the opportunity. But how can you, it's always going to be, what is it, February 17th, 21 or whatever it is. So like, how do you do that?
Yeah, I believe it's the 18th, 2021. And basically what we do is we tweak the insertion energy, the energy that we get from the launch vehicle in order to basically catch up. So it's not necessarily that the farther you go from the first date, the faster you have to go. It's actually sort of a dip. So I think 6 days after the initial launch period, that's when your C3, your injection energy was the lowest. So that's the most efficient trajectory. So we sort of started with a bit of a window, with what we call the launch period. So if you look at, this chart that I put together, if you launch in July, it's sort of a perfect kind of Hohmann transfer, which is a transfer where you basically go 180 degrees. And this is like, service level. This isn't exactly what it looks like, but
this is not to scale.
Very much not to scale. So you sort of do that 180 degree rotation throughout the solar system. But if you click to the next slide and you launch in August, Earth is rotated about 30 degrees in those 30 days. But you still have to get to the same place at the same time. And the reason that you do that is because JPL doing their planning, they're planning everything for this one day. They don't want to have to develop operations for entry, descent, and landing for every day for 30 days, so basically the later you go, that means now we have to catch up from that optimal path. So we have to launch a little bit faster. So, every day starting from now, the later we go, the harder the launch vehicle has to push. in order to get the spacecraft, going where it should go.
It's interesting. Yeah, so I guess, and maybe Tanya, you might have perspective on this, but just planning the orbiters to be in the right spot so we get the telemetry back, and then Mars has to be rotated in the right way so we hit Jezero and not some other place on there, and all that kind of stuff. So that must be why it's probably easier to change the launch vehicle parameters than it is to pick a new landing site. I guess is what I'm trying to say there, right?
Right, and actually, I just remembered that I had another visual. I had a couple of little videos to show what that looks like. So I took the targets from JPL, and so you can see from a couple vantage points. So this is imagining launching on. So those three separations that you saw, or those few separations that you saw, was launching on different days. Just leaving Earth. And if you look on the top left, it may be kind of hard to see, but you can see the launch date moving. So starting on July 17th and moving up until August 15th, it was imagine launching this day, imagine launching this day, imagine launching this next day. And then if you click to the next slide, you'll see the big solar system view of that, where you see all of those trajectories happening. And the latest one is the red one. That's a little difficult to see, but they basically all end up converging on Mars at the same time, because even though one of them started later, it ended up having a lot of energy. So this is the real sort of to scale version of the clip art version that I gave you earlier.
That's really cool.
Yeah, all of our listeners in the chat are shouting out Kerbal Space Program. This is giving me lots of Kerbal Space Program throwbacks too. Sometimes we used to do the thing where we would put the protractor on the screen, and be like, okay, I think we're ready for a launch window here, because I think we're 30 degrees off.
Right. Yeah, it's funny. I actually learned about Kerbal Space Program about 2 weeks before I got the job interview for my current job, and I was like, oh yeah, I know all about this stuff. So
because you probably wouldn't have got the job if you didn't know about Kerbal Space Program.
Right. Put me over the edge.
I know that's where I learned all my orbital mechanics from, so that's good to know.
Right.
Cool. Okay. Maybe we have a couple minutes for the burn here. If you're still good for time, could you maybe talk about trajectory corrections and stuff, and how, I don't know if you have any insight of that. Maybe your job is done now, the rocket is mostly done, but how much correction do we have to do based on the initial trajectory?
Yeah, so it really depends. I believe that they have nominally 4 or 5 trajectory correction maneuvers planned out on the way to Mars. The first one is supposed to clean up any error from the launch vehicle in order to get onto a nominal path. And then continuing on from that, they're just correcting from each one before. So, you do some to actually get onto a path onto Mars. And at that point, one interesting thing is that the Centaur, the upper stage, is going to, it really, once it separates the launch vehicle, I don't know if we'll see this on the animations from ULA, but it hooks a right and just gets out of there. So that's going to stay away from Mars. They actually do a propagation for 50 years to make sure that that's never going to get to Mars. But yeah, in terms of the spacecraft, they really just have to eat up any error from the launch vehicle, and then along the way they're just doing their navigation, seeing where they are, and tweaking when they need to. So yeah, I don't know too many details about that, but that's in general how it works.
I had an interview with when Insight launched a couple of years ago. I did an interview with Mark Wallace from JPL. Maybe you know him. So he showed me one of his papers about that exact thing you're talking about. So moving Centaur out of the way and trying to calculate what is the chance based on this new trajectory that it'll hit Mars and do a very bad contamination thing. And I've never seen so much math in my life. So I am blown away by the level of detail you guys go into for all that kind of thing, for sure.
Right. That's the constant narrative through this job. Just never seen so much math in my life, and it's always interesting because on our side, like you said, our job is kind of done in the next 20 minutes or so when the vehicle separates from the spacecraft. But there's just so much more that JPL has to do. I mean, they're looking at, I believe they're tweaking the orbit of MRO, the Mars Reconnaissance Orbiter, in order to make sure that they can track EDL, which is really interesting, right? You're changing the orbit of something orbiting around Mars in order to be able to capture the landing later. So they have so much detail that they have to look at.
Phillip, thanks for sharing all this with us. This has been really cool to learn about trajectories. It is something I think I need to get better at, because I do not understand this math very well. I know how to do the protractor on Kerbal Space Program, and that's about it. So maybe I'll bug you for some lessons. Maybe I'll come to your course. You teach, where do you teach at?
Florida Tech.
Florida Tech. Okay, so if you're in Florida, listeners, this is the guy to teach you orbital mechanics. Again, congratulations on a successful launch. Well, we're not, knock on wood, we've got a couple more steps here to go, but looks pretty good so far. Congratulations on that. Thanks again for joining us.
Thank you so much. This was great. Yeah, thanks for having me.
Thanks, Phil.
Okay, so Tanya, we are basically ready for the Centaur second burn here. So we're just kind of watching it. It's supposed to be right about now. So this is the last burn it'll have to do. This is the trans-Mars injection. This is the one that Phillip worked so hard to do. I'm looking here. This burn is 7.5 minutes or so.
Nice.
They're long, right?
Yeah, I guess it takes a lot of energy to get to Mars. Who would have thought?
Yeah. Well, and that's sort of like Centaur's like claim to fame, right? Is that it's low thrust, but it can burn forever, and it's got so much energy packed into it that it can do all these kind of great things. Anthony, maybe we can get some volume from the stream so we can figure out what's going on there.
We'll also highlight 6 major technologies that NASA is focusing on over the next decade, including the critical energy needs for such missions. But with
that we need to get out of our Park orbit.
And there we go. We're burning
to Mars. Of course, Centaur and Mars 2020 are still together.
System is in closed
as we're hearing, everything is looking nominal on this fire so far.
Right.
The main engine
looks
start
good.
was good, and the firing is going well, nominal, as we see in the animation there.
Fantastic. So this is rocket science, and it's not easy. We actually want to bring in now, we have a special guest. This is Dr. Denton Gibson, excuse me. Yes. He is a rocket scientist. His official title is Senior Vehicle Systems Engineer. Denton, how are you doing?
I'm doing well. Thanks for having me.
Yeah, did you enjoy that? Obviously, you guys
and all the masks are really
a lot
like.
Of days you guys sit on console. You have to kind of focus on your computer, but you got to see this one today.
Oh yes, and it was a beautiful launch today.
Yeah, nice sunrise. Hey, tell us about your role with LSP. I was not making up things when I said you're a rocket scientist, but what exactly do you do?
So as our role in LSP, as a vehicle system engineer, we are the engineering team lead for a lot of the rockets that we launch our science missions on. And we are responsible for the oversight and insight into these launch vehicles for the NASA.
That's awesome. And I know in the past you've supported a variety of vehicles. Tell us a little bit about the vehicles that you have supported and the ones you're focused on today.
Yeah, so some of the vehicles I supported in the past is the
Delta
we
could
2,
do. Let's
which was a long-time workhorse.
Anthony, while we're waiting for this burn to go, do you want to talk a little bit about Centaur upgrades? I know you're pretty knowledgeable at this as the Centaur fan in the room.
Not to put you on the spot or anything.
Don't tempt me about this. So
because Centaur is getting like a whole bunch of upgrades going into Vulcan, right?
Yeah, it's a whole new Centaur, right? It's based on the same tech, same tanks, same engines, but it's actually going to be ridiculously wider than current Centaur. So current Centaur is a little over 3 meters wide. The new one will be 5.4 meters wide. It'll actually be the same width as the Vulcan core stage. So what they did was, right now ULA flies Atlas V and Delta IV family rockets. And the Delta IV Heavy specifically is what's used for the bigger, beefier satellites that are going up, mostly like NRO satellites and things that really require either really big fairings or need to go directly to geostationary orbit. They're going to be able to do both of the classes of launches that Atlas V and Delta IV Heavy do today on a single rocket with Vulcan. So the new Centaur 5, it has, you were talking a second ago about how much Centaur can push because of its really high performance. It's getting a bunch more propellant. It's getting even more efficient engines because there's a new version of the RL-10. So it'll be able to have insanely higher performance than the current Centaur, which is great for the needs that ULA flies for, national security missions. But for you two, you're probably pumped about the kinds of things they're going to be able to be sent out to Mars with Vulcan Centaur in the future.
Yeah, it's explored every planet in the solar system. So so Tanya actually has to jump off right away here. She's busy Bumblebee today. She's got a lot of different streams to pop on. So we're gonna say goodbye. We're gonna say goodbye to Tanya. Tanya, thanks for joining today. I really appreciate you co-hosting with me. It's fun to have a partner to do this with.
Thanks so much for having me. I'm excited to join your first ever stream, and I hope you do more of these because this was so much fun.
Well, we'll try. It took a lot of work, apparently. So, we're going to need to figure out how to do it efficiently. But again, thank you so much for joining. I really appreciate you hanging out with us.
No problem. Have a great day.
Ciao. Yeah, we'll reconfigure and we'll bring Anthony on, and he can get his we'll get his name down on the bottom. You'll see how fast he can type out his own lower thirds here. And we are T+50 right now, and so there are about 2.5 minutes of burn left on this Centaur, and then after that, there's going to be about a 5-minute remaining coast before the spacecraft actually separates from the Centaur and heads on its way to Mars. So we are getting to the end of it here, Martians. This is pretty exciting. I'm kind of blown away about how quickly this, and there was no problem here. It just kind of went off and everything was fine. Top of the window. I love when a rocket does that. That's like my favorite thing to do.
Yeah, there you go. Dr. Gibson. Dr. Gibson is on the way. Awesome. Well,
I'm just checking in on our chat now in the Discord to see what's going on here. There's some shenanigans, of course.
So we're supporting the Crew 1 launch coming up. So we're helping commercial crew out with that one, as well as Sentinel.
Centaur, thick, yes, 5.4 meters, very, very big Centaur for sure.
So we're excited about that one.
I'm excited for Centaur 5. I'm just going to talk to you, Anthony, as if you're here still. I'm trying to think of I'm trying to remember my math for like volume of a cylinder based on the
good luck with that. I've got enough going on over here.
Well, but I'm thinking that like 3 to 5 is like probably a massive increase in volume, because the further out you go, the more volume you get with every meter, right?
I'm sure you can find a Tory tweet on that.
Yeah, it's going to be a ton of extra energy. We have a question in the chat too we can answer here. So, how will samples be found in however many years? Is there any concern of being moved or lost due to weather? So that's a great question. Malcolm, I don't have like a specific answer for you, as in someone who is smart told me. But one of the things I kind of do know is that they're going to make some decisions on the fly about whether you bundle up, 4 or 5 samples and drop them in one spot, or if you just kind of leave a trail of breadcrumbs as you go. But the point is that you can characterize the sites really, really well. That's the benefit of Perseverance, is that it's like all this instrumentation, and it's able to like really take a good stock of what's going on in the area, and that way they'll really understand the location. There are not really any concern with weather. There's not enough wind or anything to like blow these away, and so basically once you leave them there, they're probably good there for a very long time. In fact, I think the tubes are designed to last something like 10 or 20 years on the surface. They are ready to sit there forever. And then the fetch rover that's designed to go get them is optimized for speed, so it's going to land and just like deploy and just like hoof it across the surface and pick up those samples real fast using the great Canadian mobility system. How's that?
How long is this second Centaur burn?
It should be up right away here. It's like a 7-minute burn.
It's a nice long one.
It is a nice long one. It's got to hit the middle of that pork chop plot. I'm like just waiting for just like, come on.
Operation, we'll hear from Jesse Gonzalez, who's looking at the launch vehicle telemetry and watching the animation there. So let's listen in for Jesse here.
And there's the call, and
there
there's the animation again, modified based on data. So
let's
talk about communication for a minute, Nick, because it is not an automatic thing to just shoot information at Earth and have that be usable. So how do we go about communicating not only
sounds like a good
launch,
burn,
but on the way to Mars, and then once we're at Mars?
Yeah, so
all right.
The important thing is
4
when
minutes
we lifted off
for separation.
From Complex 41 here at Cape Canaveral Air Force Station, we had ground stations that were looking at the launch vehicle and tracked it all the way to provide data. Once we got onto orbit after stage separation, you heard a call out for TDRS, the telemetry network that NASA owns. which, by the way, is also used for the ISS and will be used hopefully for
Do
the
they use
landing with
TDRS
Doug
for
and
this? I didn't know that.
So getting off the ground today was great.
Are
'cause we
you?
could deconflict
Why
some
wouldn't
of
they?
that TDRS usage, right?
You got it.
But
Use it if you got
TDRS
it.
is very important for us to be able to get the
Like,
telemetry
always thought
from the
of
launch
such, like,
vehicle.
tracking and data
back down
relay
to Earth here. And then, of course,
satellites.
Mars
I always assumed they were
2020
just sort of like
is on its way to
like
Mars.
exclusively
Then
for human
the
space
GTF
flight. So
team
it was
will
like
take advantage of
shuttles and
NASA's
ISS
Deep
is
Space
what it really
Network,
used for, right?
which has been around for a long time, to be able to transmit commands and data back and forth to the Mars 2020. So it takes a lot of folks to work those, and the TDRS and Deep Space Network are very important to not only the science missions, but human
Interesting.
spaceflight
Okay,
also.
good to know.
Yeah, and I think the coordination of that is something that people don't get a chance to understand much because, as you said, we're using TDRS for.
Should have planned more
crew
content
We
for the
use
enter, I
TDRS for
think,
space
eh?
station.
Turns out, huh?
And TDRS is not an unlimited resource. We have
I
a
packed it in
number of
beforehand,
TDRS
and
satellites
then
orbit that help us do these things, but it is
I
a
don't know.
coordinated effort across the globe. Because we even
That's fine.
have ground stations in Australia, I think. Where are all of our ground stations even?
This is so exciting. I seriously, I'm just so jazzed that it went off like the top of the window. I'm
Yeah, right?
over the moon.
It's jazz, so you can take a nap before the rest of your day starts.
It's like it's been a pretty trouble-free Mars launch window. Like,
Yeah,
so
how do you
far.
feel about that? That's not.
It's like
makes me a little nervous.
yeah, it's like, are we saving the bad stuff for later? Like, I don't know. We had, basically a couple delays for Hope and a couple delays for Perseverance that were resolved, and all three of them basically hit the top of the window. Oh man.
So how quickly? So you've been busy these last few weeks, but how busy are you going to be in February? Because they're all getting there pretty similarly, right? Similarly timed.
Yeah, I think so. They all arrive in February, but what happens is different for each of them, right? And so Perseverance is just going to like barrel into the atmosphere and land. It's not even going to do anything except it's just literally going to hit Mars. Although thinking now the trajectories, Mars is going to hit it is really what's going to happen, right? Because you actually get in front of it, and then you're traveling slower, and Mars catches up to you, and you hit it, and then you land. So that's kind of how that works. But the other two spacecraft will go into orbit first, right? So the Mars Hope's going to do an orbit burn into like a big elliptical thing, and then slowly kind of spiral its trajectory out. The Chinese one, I don't know the specific orbital kind of path it's going to take, but it will go into orbit. And it's going to do like a mission for 2 months to scout first, and then the rover will detach and descend to the surface in like April. So there's a little bit of an offset for some of the stuff there, but I mean, mostly it'll be the Perseverance landing. That's going to be the big one, right?
Yeah, and the elephant in the room is how much we'll actually hear about China's mission as they go.
Yeah, we won't hear much about that at all. Okay, so we should be coming up on separation here. Oh, it's doing a little spin. Is that
little spin stabilization?
Absolutely. And Josh, we heard Jesse telling us that Centaur is spinning up. This is the maneuver right prior to spacecraft separation, where we get into a slight roll to give Mars 2020 some
stable Centaur tank pressure,
stability.
Very good performance from the RCS system, and stable indications from the avionics systems as well.
Here we go.
So RCS there, the reaction control system, that's those small, the series of those small engines that you see firing around the spacecraft. Those are used for that in-flight operations that they need. The rolling activities, as Mick's saying, is basically providing stability to the flight of Mars 2020 as we go forward. Tell us about actually...
And we have successful separation of Mars 2020 with the Perseverance Rover.
There we go.
Awesome. We got some nice applause there. That is a big moment. We are hoping to get some
That's
live
huge.
video back from that.
This guy talks faster than I do.
The time delays with communication.
I love it.
We don't have it at this instant. We're hoping we'll get to see that here in a few minutes. And we'll
All
get
right.
to you if we do.
Now, there's no other ride shares or anything on this, right?
Not on this one, no.
It's a really simple
No,
system.
are you going to be sad that there's no CubeSats that are going to help the landing sequence here?
Mission Director Center.
Well, there's a CubeSat on board, but it's just it's got legs and rotors though, so it's pretty cool. Cool. Okay, so that is separation. That is the end of the launch sequence. ULA's job is done. They put this one in the books now. They got to just move Centaur to get the heck out of the way and not send a bunch of tardigrades to Mars. But yeah, that's kind of the end. So Anthony, thank you for producing for us. This is really great to have you on and share in this this experience with me. It's really fun to do this work with you. We'll say one more thanks to Tanya for hosting with us today. She ran off to another stream, although apparently it's running late, so she's like, I could have stayed, but that's how it goes. Not everyone can run a tight shift like us, Anthony.
Well, yeah,
we had a pretty.
Yeah, you didn't exactly book the 4 guests that didn't have a lot going on today.
So that's really good. And then, of course, thank you to all the listeners, the watchers. I have to change I'm used to saying listeners, but I guess you're kind of watchers now. So thanks for hanging out with us today. We really appreciate it. This has been really fun. I hope you enjoyed the first We Martians live stream. Send me an email or a tweet or a message if you like this and you want me to do it again. We don't get a lot of Mars launches, but if there's something else that you think we should be doing, we can definitely take a look at that. But that's it. We're going to sign off and then wait for a spacecraft callback, make sure everything's okay. And thank you again. Aries.